you, those of you who are joining us for the last two talks of our inaugural EPIMP conference. I'm very delighted to have Ruobin Gong here from Rutgers, who will tell us a little bit about epistemic utility of imprecise probabilities in statistical inference. Thank you so much, Ruobin.
Well, thank you very much, Jason, for inviting me and for organizing this. It's a great pleasure to be here with you, with the group at the inaugural conference. I think this title of my talk is a little bit of an overstatement of what I'm about to talk about. I should preface this by saying, I'm a statistician and I work on, or at least I try to work on foundations of inference and also imprecise probabilities. Some of my statistician colleagues might think that, I worry too much sometimes about foundations. But, to an audience like this one, who are all experts on foundations and imprecise probabilities and so on, I feel like a lot of times I'm going to play and put on the hat of the applied scientist. I'm here to seek advice from the theorists to tell me how best to conduct inference, what are the best ways to go about choosing models and try to use principled ways to conduct statistical inference. And this is what I have come to realize when I utilize IP in my own work, that there is really this need to understand and to quantify the epistemic utility for IP in inference. As we know that, let me see if I can advance to this next slide. Yes, so I have spent the better half of my PhD career to worry about specifically, Dempsey-Schaeffer theory belief functions. That was my starting point of thinking about everything IP, and I start to realize that this is something that has been really, it's never really a major point of focus in the whole statistics literature. I think it's fair to say that, but however, IP has proven to be very useful in many aspects of inference, especially in capturing the kind of, I would call it structural uncertainty, but basically the kind of uncertainty that probabilities cannot express. And this is the motto for the SIPTA community, that there's more uncertainty than probabilities, which is very deeply ingrained and manifested in various aspects of inference. And as a statistician, we talk about the aspects of a model, including the prior, if you're a Bayesian, and there's IP. IP really manifests itself in the literature of robust Bayesian. That when we think about, we're not quite sure which prior to put on. Maybe we want to be robust against misspecification. So let's think about a neighborhood of priors. We could use IP, belief function random sets, to represent missing data and coarse data. We're going to see examples of that that I'll talk about. And there's a whole, array of different literatures on how to use IP to represent model structure. Now, Dempsey-Schaeffer theory, of course, is one of them. This is kind of where my, excuse me, let me silence my phone. Dempsey-Schaeffer theory is one of them. This is where my training was from. And then inferential models, which is, very much like Dempsey-Schaeffer theory and inspired by it, that is a framework that utilizes belief functions also to conduct inference. And it marries a lot of the frequentist kinds of validity principles into the framework. You can use IP to conduct robust frequentist inference, and this is the earlier work of Peter Huber and Strassen. And then they proved this. They have this very nice minimax, most powerful, uniform most powerful test for classes of hypotheses that are represented as Choquet capacities of order 2. In econometrics, there's a lot of instances where people worry about partial identification of parameters and also incomplete models. These are the situations where even if you exhaust all the data you could hope to observe in the world, you won't be able to identify and pinpoint the parameter of the model precisely. And there's also this aspect, which is kind of new, and I've never seen this talked about in the IP literature, but this is something that I have, in the other part of my work life, do a lot these days. Statistical disclosure limitation and differential privacy, they are in fact rooted in ideas of IP that I hope to show you a little bit later today. So these are all the different variety of aspects that IP could become useful. And for those of us who see it, it's very obvious they are, but at the same time, it's difficult sometimes to convince others to really demonstrate why that is the case, that we might prefer an IP model, because we could be asking for trouble. There are associated computational and other kinds of implications when we invoke an IP model. So this is just a slide. I really borrowed this from Jason's presentation at SIPTA 2019, where Jason talked about this is the Levi's framework of understanding the epistemic utility of belief. And this is a quantity that is labeled as VK relative to a world W. And this is going to be a convex combination of two aspects. One is EK of W, which is what's called the truth value of K at W. So this is essentially a 0, 1, is K a true belief or not relative to this world? And there's this other aspect, which is the degree of informativeness of K. That is this function T. And A here is just a measure, a relative priority that you can tune between how much do you value error avoidance versus truth seeking, right? So this is something that is very intuitive. We can talk about how to choose the functions E and T, whether we should be using the proper scoring rule for doing these and all whatnot. So these are all the potential things that can be developed into this full theory for the epistemic utility for IP. And the question that I want to ask and pose to the audience really is, how do we really formulate this VK quantity when we are thinking about utilizing that to advise a typical statistical modeling task? My viewpoint here really is that I'm going to tell you about a few of these instances, case study stories, if you like, that illustrates aspects that I think would be desirable for VK to be, and situations that I would really need the advice from VK, and then hopefully to get some of your thoughts about what might be a good direction for this to go, and hopefully we will have something very concrete for me, to convey to my colleagues. IP sometimes is a good idea, and so that's kind of the plan. So let me just start by giving you two examples of how intuitively this idea of VK as a quantity that measures the epistemic utility is manifested in statistical inference, whether it's a precise kind of inference or it's imprecise. So when we talk about uncertainty quantification in statistical inference, you don't need a BIP for this. You can just have a simple probability model. You can be a frequentist, in which case you'll be using a confidence interval to quantify the inference for a parameter or a future observation and so on. Or you can be a Bayesian who care about Bayesian frequentist reconciliation. You want to be calibrated. In these cases, the interval that you produce will ideally have both properties. One of them is that you want to have the right coverage probabilities. That is, if the parameter is indeed of a certain value, then you want this, over repeated trials of sampling your data, you want this procedure to have the probability of the interval to have the correct probability larger and never below the stated probability to cover this parameter value of yours. And in addition to that, this is not all there is, right? We also require that the interval or the region that you give to be small, measured somehow in some kind of maybe Lebesgue measure or something else. Oh, and you also want it to be sensible, meaning that you want to be able to interpret this interval, right? So this is an issue when we have a, say, multimodal posterior. Do we want to just go for the highest density intervals and give people isolated regions? Or do we still want to somehow give a connected regions that cover the multi-molds, but still meaning that they're connected? So this is something that really is reflecting some kind of a preference from the data analyst part in choosing the interval or the shape of the region. And we also might want to have the interval to ideally be bounded, right? We don't want to be the procedure to, with a certain probability, be everything of the real line, which is indeed the case if you think about how to do the Behrens-Fishers type of problem. So those are the kind of things that that are in the back of our head. It's never really written down as a formal quantified thing, but when you choose intervals, you want to do these things. And it's the same. It's similar when we go to IP, and IM is a quite self-contained framework that talks about indeed how to use belief functions to, or rather predictive random sets to draw inference and to convey inference. And IM talks about these two important principles. One of them is called validity, the other is called efficiency. They're really kind of mirroring these this truth-seeking E function and the T function here, very much like the coverage and then the smallness as before. So validity in the IM language would mean that if I'm using the random set S to describe this is where I think the parameter theta might lie, then the belief that I assign to every set A that is given by this random set should be larger than 1 minus the nominal error rate alpha, if it is in the case that my theta is not in the set A, right? So this is very much a coverage, probably just that instead of a single confidence interval, we're talking about a belief function, which is also characterizing the distribution of this random set. And efficiency really just says that, you know, given that both S prime and S are two random sets that are valid, I want the belief, essentially what this means that I want S prime to be as compact as possible. I want to put more belief in every set compared to the other one, so that given that if they're both valid. So this is the kind of validity and efficiency that the IM framework go for. And you can see that they are kind of essentially expressing some kind of desirable features for the E function and T function. But this is not set in stone, or at least I do not know if there is some kind of a unified theory so far that describes how we should construct the VKW in general for statistical modeling. So here are several things that I think would be, you know, that we should take into account, and I'm really advocating for these things to be taken into account when we construct the VK for inference. The first and foremost is, can VK, this epistemic utility, aid IP model choice? By IP model, I mean IP as well as P, so precise and imprecise model, probability model choice. And in particular, I would like to know when shall we think of an imprecise probability model to be superior in terms of its epistemic utility as opposed to a precise probability model. So this is something that is rather key that I think a theory of utility, epistemic utility, should be able to deliver. Now, I think the second aspect of this concerns the dynamic evaluation of the epistemic utility, and this is going to be related. This aspect is going to be related to what Seamus and also Teddy's talk discussion later on about, you know, how to understand learning in the context of inference versus you know, towards seeking coherence. Those are maybe two slightly different things. So we need to know how to understand this evaluation as we update information in light of new information. So that's the second aspect. The third aspect is that, and this is something that I'm putting out there as, you know, something that's maybe a little bit you know, far of a goal, but sometimes truth seeking in a statistical task may not be desirable. And this is something I learned by working in the topic of statistical privacy. And privacy, we may not want to go for truth seeking. This is something that individual confidentiality, the value of an individual data point, is something that we actively go out to conceal from the others. So this is, in a way, kind of creating a moral desiderata that is, in a way, going against some of the scientific ones that we typically are used to. And this last aspect, which with an asterisk on it, because I'm not gonna talk about the details in any way, is about computation. So typically IP models are much harder to compute. And you know, I myself spent a lot of time to think about how to make even the moderately sized Dempster-Schaeffer model to be able to run. And this is the kind of computation, or that's not computability like what Gert and many of you are familiar with. This is not, you know, the kind of, you know, can we ever be able to compute this kind of thing? We're talking about computation for IP models that are in the sense of, if you give me infinite, well, if you give me the kind of, you know, computers that Google or Facebook might have, I can compute this for you. If not, if I'm left with my laptop, I might have to take 200 years to give you an answer. This is the kind of practicality, right? That it's not supposed to be an epistemic utility considerations, which is why in the title I'm having this bracket here. But on the other hand, it is also part of knowing, right? If I have a model and the doctor wants to know whether this set of genes is associated with the cancer patient, and I say, only give me 150 years, I'll tell you the answer. I don't think there is anything epistemic about or contributing of if I have a model that really requires so much time that is beyond reasonable to produce an answer. So I think computation is something that should be taken into account. Although I do recognize that this may not be something that, from a purely theoretical perspective, we should think too much. So there is that. So these are the things that I think are important when it comes to thinking about the epistemic utility of IP and statistics. And I think for the time that I have, which for the rest less than 30 minutes, I hope to talk about these three aspects. These are called case studies, but as I said, stories that hopefully we'll be able to draw some kind of moral at the end of it to understand, there are certain things that, ideally our theory should be able to encompass. So let's start. The first one is about, how to, when we use IP to capture total evidence in hypothesis testing. The second is about the updating rules, which is the idea of, how do we really describe the dynamic aspect of learning. And the third one is the rather esoteric aspect of differential privacy, which I have less about to talk about, but I hope to show you because I think it's a really interesting and very timely connection to the IP literature. So total evidence. So this is really following the work that Teddy and Jay and Mark and we wrote this conference paper for SIPTA this past SIPTA, that we discussed the situation of paying attention, or we advocated for paying attention to the total evidence when it comes to statistical modeling. So the idea is that, for a rational agent, right, if we have an observable event F, and we denote it to be that, and then we denote K sub Tm of F to be the event that the agent learns at time T by method N, the F obtains, then the agent's corpus knowledge, the entirety of knowledge or evidence that the agent has at time T would consist of both parts. One of them is F, the observable event, as well as the fact or the metadata, talking about the fact that the agent had learned about F. Now, this is, of course, something that if you want to really be thorough when it comes to modeling, you should really construct a model or your credence function that takes into account both aspects. But this can be really difficult. And the difficulty really comes from the fact that there is going to be what we are calling epistemic entanglement between the K of F and F, because K of F is a function of F. So if you really want to model this accurately, we don't really know this is always going to be doable, because even just think about the space, the structural impossibility sometimes of being able to lay out a model that has both K and F and K of F on them. So this is the kind of problems that might just be challenging when it comes to actually practicing what we preach, which is to take into account total evidence. So we motivated in our paper for SIPTA there are situations in which a rational agent might be able to cleverly identify a observable F, so that this F is sufficient for both the event itself as well as the fact that the agent learned about it. If we have that, then there's a sufficient reduction, and we no longer have to worry about this metadata, which is the fact that the agent learned about F at time T through method N, and then we can simply worry about just modeling the observable event itself. Now, of course, this is a little bit wishful thinking, right? Because we're asking the agent to identify something rather cleverly. And the price that we pay here is that instead of having to worry about, how to even construct a safe space on which to build this model, we reduce the inability to model into a fact that we have to somehow use an IP tool to describe the simpler credence, which is something that we can describe. It has a well-defined state space, hopefully, but we won't be able to construct a model for this precisely. So we talked about situations for this, and throughout that work, we pretty much assume that the agent is going to be a Bayesian because we're using conditionalization in the proper way to update our credence. But the point that we want to make, and this is what I want to talk about today, is that even if beyond Bayesian inference and frequentist inference, recognizing the total evidence as well as using IP to capture that total evidence is just as important, right? It's not to say that frequentists are not rational, but frequentist inference may not have the same kind of properties, coherence properties, as do Bayesian inference. But that's not to say that the frequentist methods have not contributed to the accumulation of statistical knowledge the whole time. Hypothesis testing, for one thing, before it became widely abused, and now that people are really criticizing it. Before that, it was something that has been useful in telling us about aspects of the world. So I wanted to give this example that is really a very old example in hypothesis testing that was described by George Barnard in 1947. This is a rather simple setup, but I am going to make it slightly more complex a little bit, and just to show you the level of complexity and how it is important to take into account total evidence, and where does IP come in, and where is that confusion about model choice in here. So this is a very simple example. A bag of chrysanthemum seeds, so these are flowers. They're either going to be, so in Barnard's writing, these are either going to be white flowers or purple flowers. I can't really do a white flower, so that's why it's yellow, but white or purple flowers. And the statistician wants to study the relative proportion of these two colors of flowers. So he decides to do an experiment. This experiment involves a lab scientist who is going to select a random sample of seeds from this bag and then sow them, and then nurture them so that they flower, and then in the end record the flowers' colors. And the statistician has devised a very classic Fisherian test for a null hypothesis about the proportion of these two flowers. And the way to do this is that after observing the outcome of the number of flowers of each color, we're going to define what's called a reference class, which is a set of events that should be considered as of matching or exceeding significance compared to F. So these are the potential events that are more extreme than the observed ones. And then we're going to calculate the probability of this reference class under the null hypothesis. If there are more than one null hypothesis, we're going to be very conservative and take the max. If not, this is just going to be a point null, and we're just simply calculating this probability. And this is called the level of significance. And this is again a very Fisherian type of idea. So we're going to imagine scenarios, or really discuss the scenarios and look at how this test is done. And the simplest scenario is lab scientist comes back and reports that in fact all 9 flowers are white or yellow. There are no purple flowers. 9 white flowers, no purple flowers. Okay, so this is the first scenario. And how do we understand this experiment? So let's just take a look at the sample space. What is really the sample space of this experiment? The way that George Barnard sets this up is that if you think about writing the total number of the flowers as N and the difference between the white and the purple flowers as R, we can plot N and R into this triangular shape of things, and every point here is a possible data point. This is one of the potential values that N and R can take. So the observational report that the lab scientist gave is that in fact N is 9, so there are total 9 flowers, and R is 9. So there are 9 white flowers, 0 purple flowers, so R is 9, which means that is this point over here. So this is the top right corner, that color black. So the reference class relative to this observational report is just going to be itself. This is of matching significance, as well as basically, so the reference class is the class of events that you would think would surprise you more relative to what the null hypothesis says, which is that, you know, it's going to be half and half, white and purple. So what could surprise you equally or more than having seen all 9 white flowers? That would be the only other possibility, is that had you seen all 9 purple flowers. So we're going to calculate really just the probability under this binomial experiment model for these 2 events. So that comes down to just half to the power of 9, which is the probability of one of these points multiplied by 2, and that's roughly 0.39%. So that's the level of significance. Okay, so this is very simple. It's the kind of Fisherian test, exact test that that you could calculate. So this is scenario 1. Now scenario 2 is that the lab scientist did not actually tell me everything, right? So the lab scientist, in fact, later on mentioned in passing that, oh, there is indeed an additional flower. So he really planted 10 of them, but there was one that was destroyed halfway. And I don't get to see the flower because it was it sprouted, it was growing, but it was destroyed somehow. Okay, so I don't know the color of this flower. So now the total evidence is no longer that there n is 9, r is 9, but rather there are in total 10 planted seeds, and one of them was destructed for some obscure reason that did not, so that we do not get to see the color of it. So if we think about what happens to the state space, there really is an expansion of state space from previously 10 possible values of n, and I guess 10 possible values of r, to now there is this additional column. That is to say that there are possibly all 10 trials. You know, had we done the experiment again, it could have been that there was never going to be a destroyed flower, and we could really get to see all 10 flowers. So, and then the null hypothesis now becomes a fancier version, because we're now talking about modeling not just the flowers that we get to see, but also those that we don't. So that's going to be the number of white flowers that we don't get to see and the number of purple flowers we don't get to see. Taken together, these are going to be a multinomial experiment of size 10 with the probabilities of, in fact, being white, and in fact, well, the probability of being a white flower and also successfully flower, and the probability of being a purple flower and successively flower, and 1 minus those divided by 2. So this becomes a much complex null hypothesis, and it's a composite because we do not know what is the probability of a white flower successively flowering, and we do not know what's the probability of a purple flower successfully flowering. So these are just going to be things that we have no idea about, and we're going to leave them to take values in between 0 and 1, which is all that is possible out there. And to carry this on, we again try to deduce what are the possible trials that we will regard as being more extreme than having observed 9 flowers sprouting and all 9 of them being white. That would in fact be the same old one, so 9 white flowers and 9 purple flowers, as well as this hypothetical situation of had all 10 flowers reach the flowering stage, and we have seen all 10 being white and all 10 being purple. Had all 10 sprouted and one of them was in fact of the opposing color, that would be a situation we will not deem to be more extreme, just because in fact kind of this is something that, you know, George Barner writes extensively in his own work that justifies why that is the case. But the idea is that there you actually have evidence on the other side to suggest that there is not all predominantly one color. So those are the 2 events that are being excluded in the calculation of the level of significance. So if we go about doing this this calculation and look at the level of significance, which is defined as the maximum possible probability of the reference class under the null, we get something that is a value of 1.07%. And this is essentially maximizing PW and PP freely over this quantity here, which is the probability of the reference class under the multinomial model with a unspecified values of success for both the white and purple flowers. And this, I wanted to just point out that this is indeed a IP model, because not by specifically specifying, but rather by knowing this knowledge that there was this extra plant that was destroyed prematurely, we have to entertain this model that is vacuous on these two in these two dimensions, right? So this is this is indeed a composite null over which we have to take the max to get the level of significance. And so this is scenario 2, and I just want to say, this is the last scenario, and it's a similar idea, but except that now the lab scientist confessed, because I guess he felt guilty, that the reason for the plant's destruction was not because some pests probably ate on it or anything, but rather he himself accidentally trod over it and killed the young plant. So this is kind of an oversight on the lab scientist's part. However, knowing this piece of information is very important, because it now tells me that the reason why this plant, the young plant, was destroyed does not have to do with its color. Otherwise, if it were because of pest or some kind of other reasons, I have no way to at least refute the possibility that there is some kind of a linkage, maybe genetically, maybe otherwise, that this reason of destruction had to do with the color. But it's just because lab scientists trod over it. It could really have been any one of those 10 seeds. So I will now try to entertain a smaller model than the one that I entertained before. I'm going to assign the same probability of destruction, or rather survival, to both colors, white and purple. So you can see now there is only 1 degree of freedom that's lurking around in the multinomial model. And it's again something that I'm going to let to vary between 0 and 1, because again, I have no idea what is the chance of destruction. I might have some, which I can estimate, but here I choose not to. So the new level significance is the same kind of calculation. I'm going to take the max over the probability of the reference class, which stays the same as before. And I get a value that is 0.24%, which is again different from scenario 1 and scenario 2. So what we get from this is the idea that we have so what I have really described to you are 3 different scenarios in which I would argue that we have had access to increasing richness of total evidence. In the first one, we just know what we observed. In the second one, we knew what we observed, and also something we don't observe, when we know partially the reason of not observing it. In the third one, we knew that we observed something, we did not observe 1 flower, and we also knew the reason to its demise. So in terms of richness, I would say scenario 1 is less than scenario 2 is less than scenario 3. And these 3 different scenarios led me to posit 3 different sets of null hypotheses. But these null hypotheses, in terms of nestedness, I would argue that, so the binomial model is implied by the multinomial model, which is corresponding to hypothesis number 3, which is in turn implied by number 2, right? Because this is a special case of the multinomial, whereas this binomial is a marginal model for the multinomial. So in terms of richness, depending on how you value it, becomes 1 less than 3 less than 2. So this is a different order. Now, if you look at the level of significance, this is even more mind-boggling, because in scenario 1, I have 0.39. In scenario 2, I have 1.07, and scenario 3 is 0.24. So in terms of which one is most significant, it would be scenario 3. And then scenario 1, and then scenario 2, if I'm using this very naive notion of ranking the level of significance. But none of these things, the 3 kind of rankings that I just gave, agree with each other. They're all very different. And the reason why they're different is because they were just really telling you different stories. They're just aspects of a story that conveyed very different meanings. And in reality, these 3 scenarios that I described in the missing data literature, scenario 1 would correspond to a model that's called missing complete at random, in which case I just can't ignore everything that happened to the missing data. Number 3 would be a model corresponding to missing at random. So I have a model for the random missingness, for missingness, but the missingness itself does not depend on the value of the missing value itself. Whereas scenario 3 is the hardest case, which is this is a missing not at random, so that basically the missingness probability of the missing thing depends on the value that is missing. So this is essentially the kind of thing that will not be able to validate in reality unless you run a separate experiment. So these are all the kind of models that missing data literature would entertain. You can see that in 2 of them, we would require an IP language to capture. But the question now is, how do we really try to distinguish the 2 or the 3 rather? And in reality, if we had uncertainties about, maybe we are not seeing all the data or all the evidence there is, how do we go about choosing a model? Should we go for missing not at random? Should we go for missing at random? Knowing that whichever assumption that we are making may not be verifiable in reality anyway. So this is the one question that I want to pose in terms of, is there some kind of a higher utility theory or epistemic utility theory out there that would be able to aid the kind of model choice in this scenario? By the way, I think I'm seeing things in the chat. If there is, I'm very sorry, I wouldn't be able to monitor these. So if you want to ask something or just interrupt, I should have said this to begin with. I really would be happy to.
I think that you answered the question naturally in the progression of the talk, so it's
okay. Okay, so yeah, well, thank you. But then, also as I go on, which I think I really have to watch the time now, please do feel free to stop me and just speak up. I think that would be very nice. I can't see all of you. So that was my point number 1, and point number 2 has to do with updating rules and paradoxes, and this is something that that bugged me a lot when I first started and embarked on this journey. As I said, I mentioned before that I studied with Art Dempster when I was a PhD student, and the foundation, one of the foundational pieces to the Dempster-Shafer theory of belief function is the Dempster's rule of combination, which dictates how independent or cognitively independent pieces of belief function should be combined to form a new one. And it didn't take too long for me to realize that Dempster rule really is not the same as generalized Bayes rule, but they seem to be the dominating rule for either you're doing robust Bayesian analysis versus if you're doing Dempster-Shafer theory. And to me, it was very strange because I wasn't used to the idea that you can actually choose your rules to go about updating your model. This doesn't exist if you're doing precise probability calculation. If you're a Bayesian, you go with the Bayes rule. If you're not a Bayesian, you better go with the Bayes rule. This is the rule to go with, right? But in IP, apparently you could choose rules, and these rules will lead to apparently undesirable paradoxes that will deter a interested mind in some ways. So this is something that I, described, and I want to just briefly show you. I think this crowd knows, almost too much about dilation, and I shouldn't really spend time to explain what it is. But I want to situate that in a scenario that I think is closer to statistical inference. So I want to give this example, which is in terms of survey non-response. So suppose that I had a survey that had just 2 binary questions. I want to understand whether, skiers versus snowboarders, which one gets injured more easily. So I asked them, did you injure yourself on the snow? Yes or no? Or were you a skier or a snowboarder? Let's just consider that you're one, but not the other, right? I know that you can do both, but so suppose that you're one, or even you can do both. But here is the catch, right? When I have a survey that I administer with 2 questions, it's not going to always be 100% filled and precisely. So I will have some proportions of my survey that will not have an answer, maybe because people just didn't want to tell me, or that they are really both. So suppose that I just have these numbers are completely made up, right? Suppose I have essentially the fraction of people who answered yes and answered that they're skier is 11%. And you can see that I can enumerate all the possible answers as well as the frequency so that they add up to 1. And this would mean that, for example, 20% of the people that I asked just did not tell me anything, right? So I have essentially both possible answers that they could give me, and none of them were eliminated. So that's what this tabulation means. So this is a survey that has partial non-response. And if I want to learn, suppose that now the survey and the frequencies become what I know about the situation of skiing, snowboarding versus injury. So if I want to learn about the injury rate on the snow, I wouldn't be able to answer this precisely because there are these missing answers, but I can bound it, right? If I want to know the lower probability for injury, I just go about looking at the values of, or the fraction of surveys that said yes, definitively yes to the answers, which is 0.3. So 30% of people certainly injured themselves in the snow. Whereas I can also calculate the other probability by simply looking at both people who said yes and people who did not say anything. So they did not tell me definitively no. So I can calculate the other probability, which is 64%. So this is really just a distribution, or rather an empirical distribution of sets, which in turn translate into a belief function or a lower upper probability that can be described as such. Now, if I want to do conditioning or updating, and suppose that I know that I'm a skier and I want to know what's the chance of getting injury knowing that I am a skier, right? What I can do is to do the calculation, let's say by generalized Bayes rule, I will simply compute the probability, the conditional probability of injury given ski, and take the infimum and supremum. So those are the maximum and minimum possible values of this conditional probability that is permitted by this distribution of sets. And I take that and I compute that, and it becomes my conditional lower and upper probability for injury, given that I'm a skier. Now, the problem with that is if I go and actually calculate this for given that I'm a skier, and I calculate the probability of injury given that I'm a snowboarder, I get lower and upper probability intervals. Both of them are wider than the probability of injury, which is the 0.3 to 0.64 that I showed you earlier. So this is dilation. This is what Teddy and Larry Wasserman wrote about in 1993. And this is one of the pieces of literature that I have to say that shook me up so much that I did not believe this could happen, right? And this is dilation. It means that if you have an event, if you have a partition that is made up, and if you condition your lower and upper probability by some rule over the events in that partition, regardless of which event in that partition will make your the conditional lower and upper probability interval become wider than it was before, then you have dilation. And this is strict dilation if you have both of the greater signs to be strict, so no equality. The thing is, dilation is not really incoherent. You can dilate, and I think that dilation really comes as a price for, this is something that I learned from one of our discussions of the paper, Gregory Wheeler, pointing out that dilation really is a price that you're paying for trying to be coherent at all costs. You're trying to guard against the possibility, because we know that dilation is an instance where your model, the model that you posit, or rather the survey that I have with the imperfect non-responses, is one that encompasses the possible independence model. So in order to guard against the possibility of positive and negative associations, these intervals dilate. And that is what happens when you use a generalized Bayes rule to perform updating. However, it's not the case with Dempsey rule, which is something that I was more used to. Dempsey rule dilates, but one of the things that we found out about it is that it does not dilate as much. It could, it's going to for sure generate posterior upper and lower probabilities intervals that are not as wide as that of generalized Bayes rule. So it's going to be more compact, or more, if you like narrow intervals, this is going to be something that is considered more informative for you. However, it does that at the expense of possibly inducing both Schur loss and contraction, which in my book are incoherent behavior if you are going with the gambling perspective of lower and upper probabilities. And so this is kind of the expense that you incur by trying to avoid the dilation or reduce to a lesser extent what happens to dilation. Nevertheless, and this is something that I want to point out, is that this is, again, what Seamus talked about, what you called belief inertia, right? Generalized Bayes rule cannot sharpen a vacuous prior. Geometric rule cannot. Dempsey rule can. And this is one of the selling points, in fact, that this is, why Dempsey-Schaefer theory initially started off as a extension to Fisher's fiducial inference, in that this is hope of being able to draw probabilistic inference without concocting a prior to begin with. The Dempsey rule can sharpen vacuous priors. Like it or not, this is what it does. So after all this, I think it's very most interesting that dilation is regarded as a paradox. I think in IP, or not really a paradox, but something that troubles people. But when I talk to statisticians, especially Bayesians, and I tell them, there is this thing called dilation, I get this very interesting response. And some people say, this is marvelous. We need a model that can dilate, because Bayesian models is known for only being able to concentrate further and further and further. And there's never this mechanism to self-correct, or to recognize, oh, maybe I have put in too much information. I want to step back a little bit and not be able to, and to say that, I back off. And dilation is perhaps something that they think can deliver that. So, I think this, after having gone through these explorations, I came to understand that really learning, or especially the kind of statistical learning that we have in mind, is really different from pursuing coherence, or in that we tend to value or devalue different kinds of behavior. And dilation in this case could be a sense of error avoidance, and contraction and Schur loss. While you should not do that, you should not do that at all costs, it could also be a kind of truth seeking, because it's something that makes you kind of hone in to a answer further. I mean, this is completely just very heuristic talk, but I think these are the kind of things that maybe the IP epistemic utility theory might be able to provide an answer for. I think I've gone over time, unfortunately. So I will not talk about any of this, but rather just to deliver you the punchline here, which is differential privacy. I don't know. Well, yeah, it's unfortunately I went over time. But basically what happens is that differential privacy is this, let me just get 1 minute to talk about what it is. It is a very important development, especially in the literature of statistical disclosure limitation. It's a new way to protect individuals' privacy or confidentiality while allowing the statistical agency to release aggregate levels of data. This is something that the US Census Bureau has endorsed as the formal protection technique for their 2020 decennial census, which is the one that we have just done. And this is a revolution in since 1970. So this is a big thing, and it's becoming very, very important across the board. And it's really invoking also a lot of questions about how are we supposed to think about statistical inference from differentially privately protected data. And what I want to say, and you have a slide, so this is something you can read on your own, and I'd be happy to talk to you afterwards, is that the definition of differential privacy can be expressed as a interval of measures. And this is one of the constructions of IP that is typically used for describing robust neighborhoods and sampling distributions. So this is something, if we are considering sensitivity of the likelihood specification, IOM, or the interval measures, can be helpful in that. Not only that, but also the interval measures, they're associated with what's called the density ratio class, probability neighborhood, which are very nice. These are in varying respect to Bayesian updating. These are immune to dilation. So there's a lot of good properties associated with the density ratio class, which is in turn associated with the interval measures and differential privacy is something that invokes that structure essentially. Okay, so that's what I had. And then the question that I really wanted to ask is that, and I really didn't have time to explain why that is the case, but rather there is, so privacy really is something that, if you even just think about it, there's a fundamental, it's fundamentally at odds with our pursuit for accuracy. If we want to have a precise statistical summary of something, we want it to be accurate, then it's not private. To make it private, we have to add noise to it to make it less accurate. So these two things are just this fundamental trade-off between privacy and accuracy. But privacy apparently is something that we should desire sometimes as a moral desiderata. So the question now from this is whether the IP utility theory could reflect the kind of requirements that are other than accuracy and other than what we ordinarily would pose as a scientific pursuit. So that's what I wanted to say. I'm sorry for taking my time, and I'll be happy to talk to you about any of this. Thank you very much.
Thank you so much, Ruobin. Could you pull up the chat?
Yeah, Miriam has a question.
Okay, Miriam, you're up first.
Okay, thank you so much for that. That was it's very exciting for me to hear from like someone in the sciences who's thinking about IP and epistemic utility theory and all that.
Thank you.
I was just wondering, so I guess this could apply to any of the examples you were talking about, but like take the case with the flowers. So you kind of were asking this question, you showed that there were these three different ways of going, and you were kind of asking this question about whether or not imprecise epistemic utility theory might sort of bear on which of these ways we go.
Mm-hmm.
And I was just, could you tell me a little bit more about like, what is the kind of output that the sort of scientist is looking for? So what are they, is it that they're trying to decide on which of two theories to accept? And it's going to be like, we accept this one and reject that one. And then if we accept this one, we'll proceed as if it's true and like throw that one in the garbage.
Right.
Or is it that like, they're trying to have a belief state and there's a question of like, they want their belief state to be as accurate as possible? Or is it that they're trying to make a decision about which seeds to buy for the purposes of doing some experiment? Could you, so, yeah, I feel like what the output is going to bear on this. Tell me a little bit about
that's a great question. I can't pretend that I'm going to do justice to my colleagues who work on missing data modeling and causal inference and so on. But what my understanding is that a lot of times people are pressed to make assumptions about the missing data. Missing data is ubiquitous. There is everywhere. If you want to do modeling, you have to model it. But to what extent do you want to model it? So a lot of times it's some kind of a debate between this model, which is a missing at random model, which is the best they can do without having to assume too much, and the missing not at random. I think, to be honest, many people will say that, to be honest, there's nothing that is missing quite at random. It's always missing not at random, but we'd rather not think about it, because it will just make a nightmare of a model that we cannot, maybe it will give us answers that are just too wide to be turned into any kind of decision. So there is this struggle of, typically you don't want to assume too much complexity, or you want to ignore some part of this information, or that you can model, but cannot do a good job at modeling. And where do you draw that line? Where do you try to concoct something that is just manageable in terms of building and computation, at the same time to give us an advice to people? Maybe this is data that has already been collected. What can I, think about the natural experiments that just won the Nobel Prize, right? Think about the Invens, Agnes, and Ruobin, framework of try to learn about the causal effect from natural experiments. There will be missingness. I don't know why they're missing. I can only think about possibly assuming a model to construct to describe that, but I also don't want to imagine too much so that in the end I'm left with too wide of an interval. That's kind of what this is about. And what you said about do I want to eventually make a decision? Do I want an interval? Do I want to turn that into an actual seed buying thing? That's all possible. It depends on eventually who we are talking to. Am I speaking to medical scientists? Am I speaking to the agriculturalists? But it could go on. Eventually, the statistics turns into a decision, and it has to be a finite dimensional. I can either buy, sell, or hold, or there are just so many possibilities.
Wonderful. Okay. There are a number of questions in the queue. I don't know if any of them are follow-ups. If they are, pipe up now. Otherwise, we will move on to Matthias. Okay, Matthias?
Yeah, thanks. Can you hear me all right?
Yeah.
Yeah, okay. So thanks. That was a really fascinating talk. I really enjoyed it. And I just want to, it's actually a bit of a follow-on on Miriam's question. I've been thinking about the value proposition of imprecise probability recently in the context of decision problems. And I think it makes a lot of sense to try to constrain this a little bit. You've given lots of nice examples, but I think thinking of it in terms of decisions really help. So the kind of question I've been asking, I'm interested to hear your views and maybe also the views of the people in the audience on that. So the question I've been asking myself, say that I have a really practical decision. For example, I want to build a wind farm somewhere out in the sea. Okay, so that's a business decision. Imagine a business having to make a decision. Now they can choose to do, say, a traditional Bayesian analysis or whatever it is, and they come up with, they maximize their expectation. They come up with an optimal decision. Or they can, maybe there are some aspects of the problem that are not so clear, and they want to be a bit more careful with their assumptions, and they could do an imprecise analysis at some extra costs, right? So that would be harder to do. The computations are more difficult. And what they get is maybe a range of decisions. So from that perspective, presumably that range, if you did your precise analysis correctly, the range will include the thing you did with your precise analysis. So if you're then trying to sell the use of imprecise probability to the business that's having to do this, what is the value? Can you quantify the value? And if you really think about it, the value in terms of like, will you make more money if you do that? I think that you cannot answer that. So there is, I thought about this, and I think this is the right answer. So, but I'm happy to be. Actually, I want someone to tell me I'm wrong.
I understand. Yes, exactly. I think that's the trouble that I've been having.
Yeah.
The thing is, I work with these, the data users of the U.S. Census, and here is what it is. Even when you're doing precise probability, you give people an interval.
Yeah.
A lot of people are not even used to the idea there is going to be an interval.
Yes.
The census is definitive. It's a ground truth. And there's one number, and this is the number by which we're going to allocate money and distribute resources and everything. There's not even, so we're actually talking about 2 steps ahead. Right.
So I wasn't quite finished yet, because I mean, I don't want to be all doom and gloom. I think there is value to this, and the value that you have by doing the imprecise analysis is that you increase your confidence in the conclusion. Like you're doing a more honest representation of your uncertainty, and therefore you're more confident about the result. And that is a psychological aspect, but in some decision problems, this can be enormously valuable. So I think there is value there, but maybe the way that you express that utility, it's not obvious how you would put that into, like you presented a mathematical framework at the start, with which I'm not familiar, and I wonder how that could play into this. And I'm also interested to hear from others in the audience if they have thought about this problem, and what their thoughts are on this. But if there's like some hope for like saying, oh yeah, you're doing imprecise analysis, you're gonna make that much more money, I think that's hard. The thing that I hear from some people who actually do this, who know very little about imprecise probability, but kind of understand the intervals, is that it allows them to make decisions that they would otherwise not make, because they are more confident in the conclusion, because they know they have better mitigated the risk. And so they could make more money. But that's kind of also hard to put a number on. So.
Mm-hmm. Well, the one example that I can think of is, the 2016 U.S. presidential election. I think all the pollsters got the predictions extremely wrong, and I think a lot of the general public, including myself, was misled into thinking that it was a done deal, and it was going to go one way. And in fact, part of our shock, or the fact that we were in fact dealt a different result, part of that, had it been more, the pollster had them entertain these IP models a little bit more about the non-responses, about about those, then maybe it wouldn't have been so determinately, it's going to be 97% Clinton like everywhere.
Right.
So I think you're talking about the aspect of trying to deliver the degree of informativeness of the utility. On the one hand, you can say I don't know nothing, and you should anything is possible, but that's not helpful. So you want to find that right balance in between.
I see Catherine. Yeah, I wrote your comment. Yeah, I think Catherine made a very interesting point. And I think, yes, I think Miriam also wrote something. Thanks for that. I don't want to keep the discussion going. I think we could discuss this for a very long time, but I thought I bring it up. But I'm happy to move on. Thanks for your answer. It was really interesting.
Yeah. Thanks for the question.
Yeah.
So, hello. So my question is really just like an invitation for you to say a little bit about these sort of computational aspects. So in particular, how much more expensive, computationally expensive are these IP models? And are there cases where they're actually quicker to run than the precise model would be?
Well, there are two ways to think about it. If you're going for the robust Bayesian kind of way, you have a prior, and then you want to kind of perturb the prior class and just to see how much it varies in the posterior. I think what you have to do is, and this is typically done in sensory analyses in say these causal inference kind of papers that I know of, you will just basically compute whatever the model that you're computing, but using different priors. So you're doing them, and then it's not going to be absolutely getting the bounds, but you're kind of sampling the different priors to begin with and to get a sense of it. If you want to do this the proper way, which is the Dempster-Schafer kind of way, I can tell you we have just written up a paper that talks about how to sample from one of our Dempster's 1968 model that draws inference from for multinomials. And we can now do this for an adequately sized dimension, adequately sized data, but this is 60 years of getting to a Gibbs sampler that could do something in the order of thousands and of data and hundreds of categories. And this is recent work apparently. So I'm not kidding when we say that computation is really a hurdle. And I think a lot of this comes to the fact that statistical inference is not decision making in 2 or 3 spaces. We have a continuous parameter space, maybe in D dimensions, and if you want to do random sets on that, it's non-trivial. It's not something that is combinatoric. It's beyond combinatoric. So simplifications there will exist them, but then they're kind of a case-by-case basis, and I really have to go and derive them just the same way as I had to derive a Bayesian posterior and try to get a Monte Carlo algorithm to work for every one of them. So it is difficult in that sense.
Thanks.
Great, Kevin.
Okay. Hi. Yeah. So about this question about dilation and whether or not epistemic utilities for IP can kind of sort of help with dilation or sort of contraction kinds of things, by sort of not necessarily forcing you to dilate, or perhaps like allowing you to sort of have different kinds of shapes of stuff in response to evidence. I do think that that's definitely something that can happen. I mean, in particular, right, when I was working on the for 2D, I had these like accuracy scores for like two-dimensional sets of desirable gambles that I sort of was calling like selecticize accuracy. And the reason I ended up calling that is because by the way that you were sort of choosing to trade off like this like seeking truth and avoiding error, you could actually choose like basically, so if you want to go precise, right? So you get all of the like half space, like all of the like planes. If you sort of chose the opposite, you get the vacuous, and you can choose any sort of like size of cone in between that you want. And then of course, like once you do that, right? And I mean, so I can't generalize it to 3D. Like I just think it's not going to work. So I haven't investigated like what conditionalization looks like in it, because like it, I wanted to try to find something that would generalize. But it certainly will be true that like whatever kind of updating rule you get in that will not, right, obey the sort of generalized Bayes rule. And in particular, it will force you to pick things of the same size because like, that's what you've selected for. So they're absolutely, I'm like very convinced that if you, right, if there's, I mean, I think there should be in the 3D case, some ways of like partitioning the like choice of scoring rule that will be roughly like correlating to something like size in some sense of like, like how risk averse are you? And I think it will force, or like, you can force different shapes if you want to, I'm pretty sure.
Thanks. It's interesting. I think the issue of dilation, I just never was able to put that correctly in a corner of my mind. It's not a violation of coherence. It's something that should be allowed, but then nevertheless people seem to kind of upon seeing it feel like this is not right. But there's nothing in the book that says that we should avoid it, right? It's something that if you give it the correct justification, it's something that can be desired, I think.
Yeah, I mean, the evidential story seems pretty reasonable in a lot of these cases, right? But you might still think like, well, but actually still you have a preference for being more precise, even if that's like riskier, even if you know you're risking more error, and then maybe you can do that for some scoring rules.
Great. So.
Great. Actually, this is a nice follow-up of Kevin's question. Just to invite you to say more about dilation and contraction. And I was very intrigued by your hypothesis that dilation might have to do with error avoidance, whereas contraction and Shor loss may have to do with truth-seeking. And the first sort of clarificatory question is, somehow intuitively, I thought that may not be what the Bayesians were saying, because it seems that according to the generalized Bayes rule, you can get contraction as well as dilation. So seems like they were just comfortable with dilation when they happen. And that's not, I was just wondering what's your general thought? Maybe I was misunderstanding something. And what's your general thought behind that hypothesis? And relatedly, I was thinking that, well, at least in the precise case, you might think basically we've already have a trade-off between truth-seeking and error avoidance when we're trying to maximize accuracy. The thought is, well, that's why we're not always assign credence 1 to everything, because we do want to avoid errors. So just generally sort of inviting you to say more about sort of the thoughts behind the hypothesis that contraction and dilation might have to do with error.
Right.
Truth-seeking.
Right. Yeah. I whatever that's there, it really is a hypothesis and it's no more than that, because I really don't know anything concrete behind what was stated there, other than that this is just a general feeling, seeing that generalized Bayes can only dilate, but generalized Bayes cannot contract. It cannot induce Shor loss, of course, we know that, but also they cannot contract. And to be able to do those, and then to minimize dilation, Dempsey rule can do the other two. So it seems to me that just by seeing this kind of a thing, it seems that those two things are on the contrary side. And if I have to understand it, that generalized Bayes rule is something that would put 100% of its value on avoiding anything that has to do with losing or contraction, which is, I think, is also a version of losing. where Dempsey rule is being more kind of, maybe it's kind of it's not, I wouldn't say half and half, but it's not so extremely going one side. I think that was essentially what made me think maybe this is what it is, but whatever this is stated, it cannot be the Dempsey rule just cannot be understood within the context of assessing the coherence of the prior and the posterior knowledge that you put into the model. It will fail everything. But then again, it seemed just to be doing something different, because if essentially it really is a generalization to the kind of likelihood kind of computation that we do, because we multiply evidence all the time independently, and the independence is something that we assume, but we never seem to pay attention when it's just precise information. And the extreme case of the Dempsey, it really does push the belief on the parametric versions to agree with the Bayesian version, or the likelihood. So I don't think it's doing something that's completely crazy, but then it is indeed something that cannot be understood squarely within the kind of framework that holds sure loss as the ultimate sin, and because then we wouldn't be able to understand it. I really just that's all there. I really don't have more to say. I think it's a very, you picked on the question that I don't have a very concrete answer for, but it's really, it's interesting. No.
Great. Jasper? Hi, Ruobin. So there's this question of how much imprecision should we be building in? What's the right amount of imprecision to be building in? And this kind of trade-off going on. For example, with the missing data, should we be very conservative about the missingness process, or maybe we should be very precise? And I kind of want to throw it out there that we don't necessarily need to choose an amount of imprecision. There's also there can be lots of value in seeing how the output changes, like depends on the amount of imprecision that you're putting in. And like if I think about Matthias, who says like we should be thinking about like the decision perspective, and that clarifies. If you look at not at really statistics, but more like classification in an IP, then you also have this thing that you try and classify, and if the more precise your model is, then your classifier is often gonna output one class. And then if you choose to be more imprecise, then sometimes the classifier is going to say, oh, I don't know, one of these 2 or 3 options. And so you have the same trade-off going on there. And it's been long been a debate, like, okay, should we be more imprecise and then output like several things, and we say we don't know or not. And then one more recent aspect I think that has been helpful there is that you can also look at you just start to increase the imprecision in your models in some aspect where you might want to build it, and you increase that continuously. And so the precise model says this is a class, and then you go and look, if I make my model more imprecise, what's kind of the point at which the model says, I don't know anymore, now there might be kind of like 2 solutions. And that point, like if that point is far away, if you can allow for lots of imprecision while still getting to a single answer, that's kind of it's sometimes called robustness. It's like right. One number that you can kind of add to this precise output that you're still just giving, but you add this robustness information to it, and then in the classification case, this number happens to, it's kind of, we don't really know why, but this happens to correlate very nicely with the accuracy of the class that you're providing there. So it's really a useful number that tends to correlate with the actual accuracy of the, and so if you now move to statistics, and then we go to people making a decision based on what you're outputting, then you could, I don't know whether they do that or whether they look at it from this perspective. If you look at the random missingness data case, you could also think like, okay, let's just see how much lack of knowledge about the missingness can I build in until it starts having an effect on me making a decision based on what the statistician is saying. And then really, I mean, what Matthias is saying, this is gonna have an effect, and rightfully so, on the decision making. This is really a measure of confidence, I would say, in a different sense than the traditional statistical notion of confidence, like a different kind of take on confidence, like a model uncertainty take on confidence rather than a probabilistic uncertainty take on confidence, but equally valuable, and in the classification case, equally useful. And so I think that perspective is very like enlightening and underexplored. And I was wondering whether this is in the statistical community interesting, or whether people think of that, or whether IP is being thought of. And it solves this question of which IP model should we use? Like that's out of the picture then. It's just like, how IP can I go before this I don't know anymore?
This is super interesting that you mentioned this. There seems to be this correlation, so-called, with the sensitivity or the lack of sensitivity to the accuracy of the model. It reminds me of the saying that, you know, if you did a really good experiment, you don't need statistics at all. I think this is there's something that happens with that. No, but seriously, if you think about this, right? So if you just look at the example that we had, you have 9 flowers, all of them are one single color, and you're missing one. And if you just look at these numbers, they're, you know, they differ mildly in value, I said, because they are really not that different. So if I were to think about the two different, you know, if I used, you know, 5% or something, how much of a difference did that make? Because it did have a very strong signal coming from the data. It's 9 flowers, all of them in the same color. And what does that tell me about my hypothesis of equal proportions, right? So I think there is a lot to be said about, if there's so much information from the data already, then your model input, how much you change that should not really tarnish as much from a decision point of view, because the model itself is so loud. The data itself is so loud. So there's something, I think that the intuition is there, exactly as you said. But you know, again, this is you're kind of working towards a framework to say that when is it so that I can eliminate my whole IP model itself. So it's kind of working towards your own destruction. Which is not a bad thing, I think, in terms of helping the decision to understand exactly what went behind it. But yeah, I love that idea very much.
And it also helps, like, because if you're talking to the precise people and you say, but you should decide not to know, they're like, yeah, sure, but I mean, no, I'm sticking to knowing. But now you can just give the same answer you always gave, but then add to that kind of this new aspect, and say, look, I give you this extra piece of information that this is still what you always get, right? Maybe you shouldn't trust it too much in this particular case. And then, okay, the question remains, what should they do with that information? But I mean,
that's your due diligence, right? You have actually thought about it hard and decided that even if you were to entertain other possibilities, this is still the right advice you're going to give people, and that really means that it's a good one. I think this is maybe how you justify the value of having to go through that whole circle of thinking about the IP model behind it.
Yeah,
there is I agree, but there is, I think, a kind of trade-off that you need to make. I mean, once you get to the boundary of like, okay, adding more precision now takes away from the now I'm starting to sort of compromise the precision of my advice about what to do. Then I think it's not obvious that you ought to stop there. I mean, I think you need to make a kind of value judgment about, well, okay, is this a kind of case where we do care a lot about avoiding error, and we should put a little bit more in precision in our model, and then we should use a kind of safety a decision rule that gives us less advice plus a safety criterion or something. I think,
sure.
Yeah, but I mean, I think
maybe they will come asking for it. Like, you give this confidence number, and then they start to feel uneasy. Like, I don't really know. So what happens if I'm not so confident? And then maybe we can do proper.
Well, let me thank you a ton, Ruobin. I should say, Snow and Ruobin, since we talked at the Rutgers Probability Seminar, there's been a lot of development of the kinds of scoring rules that we're using in different directions. So we should have a conversation in the future where we talk in more detail about how we might use some of those to address some of these questions. But now let's thank our speaker.
Thank you.